So this relationship, the change of the boiling point, is equal to, directly proportional to, the concentration of the solute in molality times the Van't Hoff factor, to give the concentration of the solute particles, times the proportionality constant that is dependent upon the solvent only. We know that for boiling point, that as we add a solid, a non-volatile solute to it, that the boiling point will increase. So we're going to add this change, this increase of temperature to the original solvent boiling point to give us the boiling point of the solution. We have similar equations for freezing point depression. Where the change or the depression of the freezing point is equal to the molality of the solute times the Van't Hoff factor to give you the molality of the solute particles. These two are directly proportional, and our proportionality constant Kf, the molal freezing point depression constant, this is dependent only on the solvent, not the solute particles. So we have a proportionality constant that is dependent only on the solvent. And we know that this is a decrease, so this equation does not give us a negative sign. So Kf is given as a positive, and we end up with a positive change of temperature. But we notice that depression, so this decrease of temperature. So we're going to subtract this change of temperature from the freezing point of the original solvent, and that will give us the freezing point of the solution. So here are some samples of KBs and KFs for a couple different liquids. Water is a polar liquid, hydrogen bonding. Benzene is nonpolar. Diethyl ether is very weakly polar, and it behaves more nonpolar than polar. Ethanol is polar and hydrogen bonding. For boiling point elevation and vapor pressure, freezing point depression, we can show this with a phase diagram. Starting with vapor pressure lowering, as we add a non-volatile solute to a solvent, the vapor pressure is decreased. So as we decrease the vapor pressure, that's this red line here would be the vapor pressure for the original solvent. As we decrease the vapor pressure of the solution, it drops down. As it drops down here near the boiling point, we have to raise the temperature to take the vapor pressure back up to 1 atmosphere to the boiling point. So we have an increase of our boiling temperature. Near the freezing point, we're showing this is the triple point here. At the triple point, as we lower the vapor pressure of the solution, the triple point gets lowered also. This isn't representative of, this isn't actually the freezing point here, but representative of it. So as we lower the triple point here, we're shifting the solid liquid line toward the left. So we're going to lower the freezing point. And this is showing the triple point. So this would be the freezing point up here. But as we shift that line, the solid-liquid equilibrium line to the left, we lower the freezing point. If we have a semi-permeable membrane, we have them in nature in terms of cell walls. We can, of course, make a variety of these membranes. We can make them for a variety of purposes. So if we have a membrane that has pore spaces that are small enough that the solvent can pass through, but not solute particles, such as sodium ions, chloride ions. So if the solvent can pass through, it will pass through. And it will pass through in both directions. It turns out that there will be a net flow across this if the concentration on both sides of the membrane are different. And that net flow, the osmotic flow, will be from the more dilute side to the more concentrated side. So the concentration is in terms of the solute particles. So it's going from the less concentrated side to the concentrated side. And it will do this until the two sides are of equal concentration. So the net flow is to make the both sides equal, if possible. Often there will be a pressure develop. So if we're dealing with cells, cells can only accept so much water before they are full, and then they create a pressure that opposes the net flow. So the flow of solvent through a semi-permeable membrane is called osmosis. But if there's a pressure, the pressure will slow down the flow, and at some point when the pressure is high enough, it will stop the flow. So the solvent will cross the membrane in both directions. There will be a net flow from the dilute to the concentrated side, but on the concentrated side there is a pressure called the osmotic pressure that will just stop the net flow. There will still be a flow across the membrane, but no net flow across the membrane. So the pressure that stops osmotic flow is called the osmotic pressure. We're able to represent this mathematically. So we're going to use the capital Greek letter pi to represent osmotic pressure. And that will be proportional to the Van 't Hoff factor I times molarity times the gas constant times Kelvin temperature. And the gas constant isn't written down here, but it's the 0.08206 liter atmospheres per mole Kelvin. So liters and moles will cancel off with molarity, giving us our pressure, osmotic pressure, in terms of atmosphere. And the quantity of the Van 't Hoff factor combined with molarity is also referred to as osmolarity. So the osmotic pressure is a pressure that will just stop osmotic flow. So if we have two solutions of different concentrations, the solvent will flow from the more dilute to the more concentrated. This osmotic pressure, this equation here, is giving us the osmotic pressure of a solution compared with a pure solvent. So if we have two different solutions, different concentrations, the osmotic pressures of each solution here, the difference will be the pressure that will stop the flow. So this is a graphical representation of osmotic pressure. So we have a flow from the dilute side, pure solvent, into the solution. And that will raise the level of the solution. And then when the increase, which represents pressure, stops the net flow, when the increase stops increasing, it will have a net flow of 0. And that increase, there will be the osmotic pressure. So, some terms for osmotic pressure. If we are comparing solutions, two solutions, if the two solutions have identical osmotic pressures, then they are called isotonic solutions. So if we have two isotonic solutions separated by a semi-permeable membrane, there will be no net flow between these two solutions. So if the solutions are not isotonic, they are different concentrations. The one with the lower osmotic pressure is the hypotonic solution, and the one with the higher osmotic pressure is the hypertonic solutions. And the solvent will naturally flow from the hypotonic into the hypertonic, and it will continue to do so, if possible, until they are isotonic. If we take a solution separated from a solvent by a semi-permeable membrane, and we put more pressure on the solution than the osmotic pressure. So osmotic pressure is the pressure that stops flow of water into that solution. So if we increase it, make it greater, we actually reverse the net flow of the solvent. So if we have higher pressure than the osmotic pressure on the solution, the solvent will flow from the solution into the pure solvent side. This is called reverse osmosis. And this is used to convert seawater into pure drinking water. It's used on commercial scales to make water for cities, and it's used on small scales to purify water in the house. We've already been looking at the Van't Hoff factor. Van't Hoff factor is the ratio of moles of particles in solution to the moles of solute in solution. So if we have a non-ionic substance or non-electrolyte, this ratio is going to be 1 because it does not dissociate. The solute does not dissociate in solution. If we have ions, so we're going to have the number of ions over the number of moles of solute. Our first expectation would be that ionic compounds will dissociate completely, but we can measure the Van't Hoff factor, and we find that we sometimes have ion pairing that reduce this from the expected value. These colligative properties can be useful for determining the molar mass of compounds. So by making appropriate measurements, we can get the molality or molarity, and from that we can get the moles of the compound. If we had initially measured the mass of the compound, then we can easily determine molar mass. Molar mass will be the mass of the compound divided by the moles of the compound.